I suggest we move on to the next section, which is the case studies. So smart synergies for green buildings, focusing on 3 specific case studies. I suggest that the 3 speakers come to the stage, and one by one you can come up to the laptop to present your various case studies. All right. Maybe we'll start with Jeremy.
Good afternoon. You'll hear me now. Okay, so my name is Jeremy Harrison from Dublin. For those of you who don't know, we are an consultancy and research company working in transition from old energy to new energy. What we do. I'm here to talk about, the title is The Future of Smart Energy and the Smarter Part is Transactive Energy, which is one part of the energy system. So the question is, why do we need to worry about it anyway? You've heard a lot about the overall energy crisis and the Ukraine war and all of that means. I'm going to focus on one very specific part of it, and that is about how we optimize the energy system. And the importance of that from 2 perspectives. One is that as we become increasingly dependent on intermittent renewable generation, we no longer have the characteristics in the energy system which we used to get from large thermal plants, things like inertia and dispatchability and so on. I'm not suggesting for a minute that we shouldn't have increasing amounts of renewable generation. What I'm saying is we need to address the shortcomings of that with some other measures. The other side of the balance is the increase in demand for electricity to decarbonize new sectors. So it's about replacing the existing electricity for uses that we used to do in cooking and lighting and so on, but also the growth in demand from mobility and heating, and quite importantly, what's emerged over the last couple of years, the increasing, not necessarily total demand, but the location of demand as we move from central office working to home working. And so there are ways of overcoming this, and I think we've heard about it already, which is you can overcome the electricity supply and distribution by investing huge amounts of money in new generation capacity and new distribution network capacity, but it takes a long time, it's very flexible, and it's extremely expensive. So what I'm going to talk about today is how transactive energy can help to optimize that by investing in what we call non-wires alternatives. So let me start off by what I mean by transactive energy. There's a definition, I think, here, which is about a system of economic measures which optimizes the performance of the physical infrastructure. But whilst that sounds quite simple, in fact, it's relatively complex in that it depends who you're optimizing it for. Is it about optimizing it for the end user, for the overall system, for the distribution network, for the generation parts? So we need to consider that. And there are a couple of business models which I'll refer to, which are peer-to-peer schemes and self-consumption. Those are really just models of how we trade energy with one another. And I'll talk a bit more about that in a second. So if I start off with a really simple example of how the growth in renewable energy has supported decarbonisation of individual homes in this case. So in this particular example, somebody invests in a solar PV system and they use that as much as possible within the home. First of all, by using it with smart appliances like smart washing machines, and maybe fridge freezers, things like that, and heat pumps to some extent, all those four alignments. And then whatever excess there is, maybe you put that into a battery, and if you've still got some excess, you put it into anything, hot water, whatever. Now that's the scheme is optimized purely for the benefit of the householder themselves. It has no benefit to the wider network. And of course, with the best one in the world, solar PV is not going to meet the needs of that house throughout the entire year, certainly not in Northern Europe. So what could we do to leverage some of the benefits of smart control of the consumption of electricity to the wider system? So if we then look at how individual homes can support communities, this is an example of a system where, rather than each home consuming all its own electricity all the time or attempting to, they trade some of that excess. So there's the fourth part of that. So you use as much as you can in the home, then you store it. Then rather than just dumping it into hot water, you maybe offer that for sale to somebody else in your community. And that can be done also in conjunction with things like a communal storage asset, communal battery, for example. And there are energy communities, for example, who are already established to do this kind of thing, to optimize the use of locally generated electricity locally. It has many benefits in terms of not just the economics of the community, but also in terms of the overall system. If you can avoid impacts on the higher levels of the system, then you avoid the need for investment there. And the example I want to talk about today is based in the UK. It's called the local energy market in Cornwall, which is in the southwest of England. And historically, Cornwall suffered from a lack of generation capacity. And there were always constraints on new connections, demand connections, that is. Now, when we started the wind and PV revolution in the UK, people thought, well, that'll solve that, because we've now got southwest of England, first very windy, it's also quite sunny by British standards. And so we thought there'd be a better balance, that some of this generation would match the demand. In fact, it didn't do that, because you don't necessarily have a coincidence in location or in time of generation with the demand. So the local DSO, Western Power Distribution, set up what they call a neutral energy platform, local energy market platform, and in that they installed in a trial some micro CHP schemes, some PV, some heat pumps, some battery storage, and the idea was that the transactions between each of these called prosumers, the individual homes who have micro CHP, for example, they could trade that surplus electricity with somebody with a heat pump who needed electricity, and there's an excellent coincidence of micro CHP generated electricity with the demand for heat pumps. So that worked very well. But there was another layer. It wasn't just about transaction of the energy. Because WPD had grid constraints for generation and demand assets, the use of this peer-to-peer transaction meant that WPD could also put their own contracts onto the platform to request flexibility services from the system. And those became a transacted value. So that although it might appear that I was transacting my micro CHP electricity with your heat pump, in fact, I was also transacting with WPD to provide flexibility services. And that has quite a significant value to the overall system. As a consequence of that, this is, as I say, what we call a non-wires solution. So rather than just spending money on additional reinforcements to the network, additional capacity to distribute electricity, the flexibility that this transactive system, local energy market platform, provides was able to avoid that necessary investment and therefore facilitate the connection of additional generation to the system. So I was asked to just give one very short example, so that's that. I just finished to say, there's a whole load of benefits to transactive energy and flexibility. And I think for those of you who were at the SmartSend event yesterday, will have heard that the massive potential value to be generated from flexibility. I think in Europe, something like 21 billion euros in savings on distribution networks deferrals alone, and that doesn't take account of all the other benefits. They said they reduce peak customer 7% as well. Every little helps. So I'll leave it there and happy to take questions from anybody. Thank you.
Thank you, Jeremy. And I think I failed one of my first tasks as a moderator. I did not properly introduce you. You did yourself. So Jeremy Harrison from Delta E, Principal Analyst. So any questions? online as well? We do have people online. If not, we'll catch it at the end. I'll move on to our second speaker, which will be Alexandra Tudurio. She's head of policy in Europe, and she's today representing the PACE project, focusing on stationary fuel cells for homes and small businesses. Alexandra.
Thank you, Hans. I'll try to go fast, although I have many slides. So this is PACE at a glance. PACE is one of the co-organizers of this event. As Hans mentioned, it's a EU-funded project, a flagship project with a total budget of 90 million euro, which aims at bringing fuel cell micro CHPs closer to mass commercialization. And we are on track to actually installing up to 2,800 fuel cell micro CHPs that are coming from different manufacturers. And you can see here, we have a very good European base for manufacturing fuel cell micro CHPs in Europe, from Viessmann to BDR Thermea to Solid Power, Bosch, Sunfire, and Hexas, who are part of the project, along universities that have contributed towards the research behind a fuel cell micro CHP, as well as Cogen Europe, the coordinator of the project. So why fuel cell micro CHP? It has this is a relatively new technology that produces electricity and heat in your home without combustion. Mr. Kaff mentioned that we must stop burning things. Well, with fuel cell micro CHP, we are able to use gas, but also hydrogen very efficiently without combustion, which eliminates some of the NOx and SOx emissions that normally would occur when heating homes. So what are some of the benefits? Fuel cell micro CHP for consumers, supports the European energy transition and supports the overall energy system. It provides greater flexibility to the energy system and fosters innovation and high-value jobs. This is in a nutshell what we mean by fuel cell micro CHP. These units can be installed in homes and in your basement. Basically, they look either like a fridge or a washing machine, but they need to be coupled with sometimes with a peaking boiler for the coldest days, just like a hybrid heat pump would. And along the fuel cell, you would also have a heat storage to better balance the system throughout the year and maximize its efficiency. And because of this efficiency benefits, it actually reduces CO2 quite significantly, and I have some charts to show that. And beyond that, it contributes towards a more secure and resilient energy system overall. This is an overview of the installations as part of the PACE project. As you can see, we are approaching the 2,800 units mark with 2,300 that have been installed and much more that have been already commissioned. And you can see that they've been installed across Europe, primarily in Germany, Belgium, the Flemish region, but also France, Italy, the UK, the Czech Republic, some in Austria, some in the Netherlands. So as I mentioned, this is a technology that empowers consumers. We actually carry out surveys with the field trial participants, and all or close to all of them are very happy with the environmental performance, the reliability, the running costs, the comfort and warmth of the systems. We also interviewed some of the field participants. And you can see Mr. Boll in Hamburg is very happy that most of the electricity that he needs is covered with the fuel cell. And back then, this is pre energy price crisis, he could estimate a saving of up to 1,000 euros. We've also carried out some simulations on the energy bill impact of replacing your boiler with a fuel cell micro CHP. And you can see here in image picture, this is the energy cost with the micro CHP. And the SFH is a single family home, the 3FH is a multi-family home. So you can see that the impact on the energy bill is quite significant, with sometimes even half or even halving the energy bill due to the micro CHP. And that benefit or that impact on reducing the energy bill is mainly from self-consuming or self-producing and self-consuming your own electricity and avoiding electricity from the grid, which can be quite expensive. We're now looking to update this figure with the more recent energy prices. This is based on energy prices in mid-2021. But we think that the ratio, so in relative terms, fuel cell micro CHP would still actually impact in a positive way or reduce a consumer's energy bill quite significantly. And there have been studies as well comparing micro CHP and fuel cell micro CHP to other heating solutions. You can see here a range of solutions from gas, solar thermal, heat pumps, district heating, a heat pump plus PV. And in terms of both CO2 and NOx emissions as well as cost, a fuel cell micro CHP would perform quite well compared to, for instance, a heat pump. But of course, this takes into account the overall energy system, so it accounts for emissions both on site and in a power plant that eventually ends up fueling heat pumps at the moment. And then moving towards to the topic for today, how fuel cell micro CHP supports the whole energy system. We know that there's quite significant energy losses on the electricity grids. This is an overall picture of our European electricity grids, where we have 400 MTUs of energy that are put in, and only 200 MTUs of energy that comes out. Another 22 MTUs is lost in the grids, and those losses are actually represented by heat that is just dissipated into the air. And just to compare that to the whole heat demand of buildings in Europe, that's the same. So about 200 MTUs of heat is required by all buildings in Europe, and we're actually wasting 200 MTUs of heat in power plants today. And so the alternative to that is to actually capture that heat and avoid wasting that heat with CHP. Of course, CHP will not replace all of Europe's power plants. We will also have PV, we will also have wind, we will also have other sources of electricity. But it is worth considering first producing energy in the most efficient way, at the same time as we try to reduce demand as much as possible. And then when it comes to electrification, we do hear that electrification is the most efficient way to decarbonize buildings. And I've looked back at the study by Heat Roadmap Europe. This is a EU project as well, which actually simulated what it would mean to electrify all of Europe's buildings. They looked into several countries as well, and you can see here that if you do electrify efficiently with the highest efficiency heat pump, in very well insulated buildings, you will still double peak demand compared to today. So that is quite significant. And if you compare this to the emergency interventions regulation, which aims at reducing peak demand by 5%, we see here you can see we have a problem. We want to electrify, which will increase peak demand, but at the same time we want to decrease peak demand. So this is something that we need to take into account. If we also electrify too soon, so if we electrify buildings that are not well insulated, then we're looking at tripling or even bringing peak demand up by 5 times. So that's really scary in terms of building up the generation, so the electricity that we need to cover that peak demand, and also building the grids that will transport all that electricity to Europe's homes. And so our solution, or part of the solution, is of course to incentivize CHP and micro CHP in particular. CHP coincides, or CHP production coincides with the demand for electricity from heat pumps as well as EVs. And it can complement renewable energy solutions like wind as well. And I will leave you with this. This was a simulation done for 2 days in Germany in winter in 2050, so in a net zero scenario, where there's very high shares of renewable electricity. But on these 2 particular days, there were variable shares of renewables. So for almost half of the period, renewables were maybe 20, 30, or renewable electricity shares were quite low. And in that case, micro CHP played a role. And then when higher shares of renewable electricities came up into the grid, then heat pumps would be optimal to run during those hours. So just to summarize, why micro CHP? It is highly efficient. It complements renewables, it complements electrification, and it also at the same time empowers consumers.
Thank you, Alexandra. That she focused and stressed on homes, dwellings, but especially in Belgium, because our micro CHP is used by many businesses, SMEs in particular, and we have some sampling of those products produced with fuel cells or 5 units, 10 units, a modular approach in some cases. So during our reception, we will have fuel cell micro CHP produced beer, chilled. Not necessarily with fuel cell micro CHP, and chocolate as well produced by the units in Belgium. So that's something to look forward to. So thank you, Alexandra. We'll move to our next speaker, Camilla.
Westjager,
that's much better than what I was going to say. Director of Energy and Public Affairs at Veolia, and her title of her presentation will be Delivering Decarbonization at a Local Level. Thank you, Camilla.
Yeah, a little bit complicated to follow up Alexandra's presentation. Mine is going to be really long after that, but I'll do my best. So today I will be presenting to you a case study from a project that we've been carrying out in Italy, and that also shows our reflection, thinking about the reform of EPBD and the Energy Performance of Buildings Directive. Because as you all know, this revision introduces the notion of zero emission building, and we all care about this definition reflecting in the best way possible the most virtuous and the most interesting heating solutions that we can put on the market. So this precise case study shows one of the projects that we started to implement in 2018 in Italy by one of our business units, which is called CityRun, which is a really specializing in district heating and energy efficiency services. And this is interesting because it's the first of the kind of the project implemented in the country, where what is called the Technology Center, a complex plant of cogeneration and free generation, actually feeds into a municipal district heating. And it's based on an agreement with the municipality and involves several pillars, which includes a new primary technology center, a new services and laboratory center, 800 meters of underground galleries, and 13 kilometers of new district heating. The investment involved is around 113 million euros, with about 25% of public funds being provided by interested municipality and region. And this is the illustration of how the project, of the delimitation of the project. With in the circle in the middle, you can see the technology center that is quite important, a large size of the space of the territory of the hospital. So the district heating that is brand new, as I mentioned, is serves about 38 megawatts of rated thermal energy, and connects quite a number of municipal buildings, including universities, schools, one hospital, social housing, and 33 private condominiums. And there is a possibility to connect, and we have very concrete plans to connect more people who are interested in being part of the network. And just to go back to the new technology center, it's actually composed of a gas-fired heat plant, refrigerating plant, emergency power plant, and what is important here is the cogeneration units. So overall, there are 5 cogeneration units. 2 are fueled with vegetable oil, and 3 which are natural gas based. But they are, we are actually studying the possibility of running those units on biomethane, which again we go back to the issue of regulatory barriers, and this will obviously depend on what is being done at the level of the EU and Italy in terms of promoting biomethane and access to biomethane on a large scale. There is also something that I think is worth mentioning, is the fact that we deploy, in order to run this entire project, because it's quite complex, as you can see there. There's a big technology center, there's a generation center, and there's a district of various buildings connected to it, so you need to manage it. And the way we do it is we use a solution which is called HubRate. This is a specific technological solution, which is a remote monitoring center, which is equipped with sensors, and we capture both energy production, energy consumption, and based on that, we construct key performance indicators that can enable us to monitor how much energy is being used, if there are any leaks, if there are any technological problems that need to be solved immediately. And last but not least, for the electricity that is produced using cogeneration, we use a Eurocam system, which enables us to use algorithm to determine whether we have interest in selling the electricity on the grid, or rather also use it within the framework of the technological center. So as I mentioned, the project started in 2018. It was completed in 2014, and it's still in progress in the sense that we are still connecting more and more clients who are interested in being part of the network, given it's a low carbon, relatively low carbon district heating that is going to be soon converted in a green energy one. And obviously, it's difficult not to mention the concrete results obtained with this project. In particular, we have already achieved 15% savings of primary energy, which corresponds to about 30% less of CO2 that is being emitted by all the buildings that are connected to it. And the calculation is obviously based when comparing CHP to a separate production of heat and electricity. And this is all the more important in the current context where we really need to make sure that we save energy as much as we can. And going back to the introduction of my presentation, the notion of zero emission buildings, it's important that that we make sure that these kind of projects that are quite capital intensive, but also extremely virtuous because they enable us to use available energy on the level of the district, are also part of zero emission buildings definition in the revised EPBD. So we hope that thanks to events like this and discussion like this that we have today, we can make that happen. And thank you very much for your attention, and I'm looking forward to your questions.
We are running a little bit behind, but we had an extra 30 minutes of Mr. Koch, so I think that was a good thing. I'll open the floor now to questions, both the floor and online. I don't know if my colleagues have any questions that they've captured online. Just to remind everyone, we're online and in person. So if there's anyone on the floor, if not, I'm pretty sure.
I have a question to Jeremy.
This is unprecedented. Okay.
Really? So I was wondering, you were showing how the auto-consumption basically works when you couple it with peer-to-peer systems. And when I was thinking about, in my personal story that I shared at the beginning about thermal insulation of my family house, we were also thinking about installing a heat pump and a solar panel. And what we are told is that you always tailor your solar panels to the needs of a heat pump. And so I was very curious about your opinion about that, because if you do that, then you basically close the door to the possibility of exchanging energy on a larger scale, because you have exactly the amount of renewable energy that you need for your auto consumption. So do you think there is something to be done on an individual level in order to today open this possibility for the future energy communities like this?
The first thing I would say is that I am surprised that the advice was to try and match your PV to your heat pump, because there's a complete seasonal misalignment. Even if the amount of electricity you consume in your heat pump is 3,000 kilowatt hours a year, and the amount of generation is 3,000 kilowatt hours a year, it's a totally different time of year. So if you did that, you would end up anyway with a huge surplus in summer and a deficit in winter. And that's one of the attractions of having a communal community, whether it's a virtual or a physical community, where you can actually trade your surplus to others who need it when it's available. But it is one of the issues with solar PV that it's a great sort of universally available resource, but the problem with the systems is that it doesn't happen when you actually need it most. So if you've got a load in summer, great, it will meet that. But the size of your PV system should be determined by what the economics are that you want to meet. So if you want to have a larger system because you can trade excess electricity, or because you consume it yourself, SME, for example, then that's the basis. These models that I was talking about, really the intention of those is to allow you to trade your excess, but then that's in a peer-to-peer environment. In what's called collective self-consumption, you can have communities of people who come together to share their communal assets. So it may still be on the rooftop of their houses, but very often it will be a wind turbine or a small solar farm, for example, with maybe a communal battery, where that resource is allocated according to the rules of the community. And the benefit there is you've got a much more diversified demand, so that rather than trying to match your rooftop PV with your specific demand, you're taking a bigger portfolio generation, bigger portfolio demand. They're quite complex business models, and they're not as cost effective as individual self-consumption, but they're still one of the ways that the EU is trying to encourage people to invest in renewables that they can then contribute to their own consumption. Answer your question.
Don't match your solar panels with your heat pump. Build more. Thank you. Well, this is the end of the case studies. So thank you to our three speakers and the three very interesting case studies.